Okay, so if we're trying to measure the extension of a rubber band when masses are added, then we're certainly going to need a mass hanger to put our masses on. We're going to measure the extension, so we're going to need a ruler, and a retort stand and clamp to hang the whole thing off makes sense. Ammeter is clearly a joke, so is thermometer, and steel spring isn't useful if you're trying to measure the extension of a rubber band. So here hopefully you can spot the pattern of what's happening. 350 goes to 3.5, 150 goes to 1.5, so 550 goes to 5.5. If we want to know why that's happening, we've got to think about W equals mg. But of course the m in this equation must be given in kilograms, and 550 grams in kilograms is 0.55, g is 10, so the weight of the mass is 5.5 newtons, as we'd already spotted just by looking at the pattern. When we're plotting the graph for this, it's important that the independent variable, the thing that we change in the experiment, is the force, and that always goes on the x-axis. Okay, now really if you choose a sensible scale here, the rest of it's easy. So let's go with the most obvious scale that I can think of. 2, 3, 4, 5, 6, 7, 8, 9, 10, and the largest value that we've got is 10.5, so that's just about going to fit onto our graph paper, and that's the one that they're hoping that you're going to use because it makes the rest of it really easy. So of course extension, which is the dependent variable, which is the thing that we're going to measure in this experiment, always goes on the y-axis, and if the maximum extension is 24, then hopefully you've noticed that there's 12 or more squares up there, so a sensible scale to use is each of these big squares is equal to 2 centimeters. So there you can see that it does fit neatly on the graph paper if you use those scales. Next thing that we need to do is label the axes, and don't forget the units, and that gets us another mark, and then we're going to have to plot the points again. Same as normal, we need to be accurate to within plus or minus one of the small squares. Okay, so now I've finished plotting all of the points, and one point that you shouldn't neglect to plot is the point down at 0, 0. I must apologise for the state of the graph. Okay, it's impossible to use a ruler unfortunately on the tablet that I'm working on, so sorry about that. And the other thing that we've got to do is plot the line of best fit. Okay, the line of best fit is definitely not a straight line. A curve is a much better fit to this graph. Okay, so it needs to be a curved line through or very close to as many of the points as possible. Again, my curved line's not ideal. Okay, hopefully I'd be able to do a better job than this with a pencil and a bit of paper. So does the rubber band obey Hooke's law? First of all, we need to know what Hooke's law is, and Hooke's law states that extension is directly proportional to the applied force. Hopefully you know that for springs within their elastic region, Hooke's law is true. Why? Because the graph is a straight line graph through the origin. Okay, now we haven't done enough yet to get us the 2 marks, and that's because we haven't used information from our graph to justify whether the rubber band obeys Hooke's law or not. Okay, and the extra piece of information that we need to say is that it does not obey Hooke's law. Why? Because the graph that we've got is a curvy graph, it's an S-shaped graph, so it's not a straight line through the origin, so it's not directly proportional.